Hey gang, coming at you with lesson 1.6 for Math 8. You need to be on page 51, and if you need to, grab that calculator. We're basically going to just be moving the decimal point today, so if you can do a loop-de-loop with your pencil, you're good. All right, our objective today is to represent very large or very small numbers in scientific notation. It's going to make more sense once we get started, so let's get to it. Okay, real world link today. A single-sided, single-layer DVD has storage capacity of 4.7 gigabytes. 1 gigabyte is equal to 10 to the ninth bytes, which is basically 10 with 9 more zeros. All right, so basically what that means is we're going to start right here with this right here. It's 4.7, and each one of these 4.7 has 10 to the ninth bytes in it. So our multiplication expression that will represent how many bytes can be stored on the DVD for each one of these gigabytes, we are going to represent that with 10 to the ninth bytes. I don't have to find the answer, it just tells me to do an expression. Let's look at what patterns are going to happen as we multiply by 10 with a power. 4.7 times 10 to the 1 is the same thing as 4.7 times 10, and we get 47. Let's look at the second example. 4.7 times 10 squared, same thing as 4.7 times 10 times 100, so we're going to have 470. Notice how my decimal point moved 2 places this time, and my exponent was 2. In the third example, 4.7 times 10 to the third, I have 3 zeros. I'm going to move my decimal place 3 places to the right and get 4,700. In my last example, 4.7 times 10 to the fourth is the same as 4.7 times 10,000. Again, 4 zeros, 4 is my exponent, move my decimal 4 places to the right. So I'm going to have 47000 with a comma. Let's look at negative exponents. When we have 4.7 times 10 to the negative 1, that's the same thing. Remember, when we have a negative exponent, we put it down in the denominator, and the exponent becomes positive. So we have 4.7 times 1/10, and my decimal moved now to the left 1 place. In my second example, 4.7 times 10 to the negative 2, my decimal place is going to move 2 places left. So it's going to be 0.047. Third example is 4.7 times 10 to the negative 3. I'm going to move my decimal point 3 places to the left, 0.0047. Again, all I did was go boom, 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 and put my zeros right there. Let's look at the last one, 4.7 times 10 to the negative 4. Move my decimal 4 places left, boom, 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 boom. Add zeros where they belong, and I'm going to have 0.00047, and I'm sorry if I'm writing on my head, hopefully you can hear. And in here, we're basically multiplying by 1 over 10,000. Let's keep going and see if we can make more sense of this. My table is here for us to look at. Question 3 says, if 4.7 is multiplied by a positive power of 10, what relationship exists between the decimal point's new position and the exponent? So basically, guys, what's the relationship between how many places we moved the decimal point and what our exponent was here? Well, when it was 1 as an exponent, it moved 1 place. 2 as an exponent, it moved 2, and so on. So the decimal moves right when it's positive, the same value as the exponent. All right. When 4.7 in number 4 is multiplied by a negative power of 10, same question. So when the exponent's negative, what happens to the decimal point? It moves left the same value as the exponent. It moves left the same, that's a terrible the, value as the exponent. Hopefully I'm not writing on my face quite yet. Okay. Next page. Scientific notation. Let me erase what is already here, sorry. Scientific notation is when a number is written as the product, basically a multiplication problem of a factor, so some number, and an integer power of 10. So some number times 10 to some integer power, basically right here. Some number times 10 to some random power that has to be an integer. So 0, 1, 2, 3, or it could be a negative, -1, -2, -3. Just can't have it raised to a decimal or a fraction because those are not integers. So let's look at a regular example. If we see 425 million, that can be represented in scientific notation as this. Notice how it's one number, point something something, times 10 to the 8th, meaning they moved their decimal place 8 places to get to right there. All right, now huge rules right here. If the number is greater than or equal to 1, the power of 10 is positive. If the number is between 0 and 1, then the power of 10 is negative. That's going to make more sense when you see it in play. All right, let's look. Example number 1, 5.34 times 10 to the 4th. I know that my exponent tells me how many places to move the decimal. In this case, it's positive, so I'm going to move right. I'm going to move that decimal place 4 places to the right, and you can see that illustrated here. Number 2, 3.27 times 10 to the -3rd, moving to the left this time, so this number is going to be smaller than 1. 3 places to the left, you can see the bump, 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 that decimal dance, and you've got 0.00327. Try these on for size, see how you do, reference back to your 2 examples, and unpause the video when you're ready. Go ahead and pause now. All right, number A, you should have 7.42, 5 places to the right, boom, 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 742, comma, 000, 742,000. Number B, 6.1. -2 tells me to go 2 to the left, boom, boom. Put a 0, I should have 0.061. And number C, 3.714 times 10 squared. I'm going to move that decimal point 2 places to the right, boom, boom. And I'm going to end up with 371.4. In examples 3 and 4, we're actually thinking backwards here from our first examples. This says to write each number in scientific notation. So now we're going to actually figure out what the power is. So in this case, look at how they've moved the decimal, and I will highlight it too. They went 1, 2, 3, 4, 5, 6 places, and they went 6 places to the left. I know that this number is larger than 10, or larger than 1, actually is what I should really say. And so I know that my power is actually going to be positive. So they've multiplied by 1 million, this 3.725, which can be represented as 10 to the 6th. So this is my final answer right here in scientific notation. Oh, that's terrible. Forgive me. So let's look at the example number 4. 0.000316. I've got to get my decimal point, so it's right in between that 3 and 1. Boom, 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 boom. I moved 4 places. This time, my number that I'm writing in scientific notation is less than 1, so that tells me my exponent is going to be negative. -4 because I moved 4 places. Try out some of these on your own. In a second, after you've unpaused, we'll go through them together. Go ahead and pause the video now. Okay, let's look at number D. My number is greater than 1, so I'm going to have a positive exponent. 1, 2, 3, 4, 5, 6, 7. I want to get my decimal point, so there's one number in the ones place and the rest is in decimals. So I have 1.414 times 10 to the, how many did I move? 1, 2, 3, 4, 5, 6, 7. 10 to the 7th. Not enough room for me. Go ahead and write it over here on yours. E. This number is less than 1, so my exponent is going to be negative. 1, 2, 3. I've got to get it between the 8 and the 7. So 8.76 times 10 to the negative 3. Excuse me. Here, I want my decimal point to be in between those two ones. So I have to move one place to the right. My original number was less than 1, so I'm going to have 1.14 times 10 to the negative 1. Again, yours should be written here. Rewind if that doesn't make sense. We're moving on. All right, this example asks us to refer to this table, and we are going to order the countries according to the amount of money visitors spent in the United States from greatest to least. So we're looking at the people from Canada maybe spent more money than people from the United Kingdom. Okay, so we're ordering visitors from these countries coming to the United States, how much money they spent, by the most money to the least money. So the first thing we have to do is we have to put the two scientific notation values, the two same exponents, in a group. Well, I know 1.06 and 1.03. 1.06 is bigger than 1.03, so I put it on top. And I've got my same exponents right there. I'm grouping the same exponents together. Then I'm going to group my other exponents that are the same together. 10 to the 6th and 10 to the 6th. Then I look at what the first factor is. The larger one comes first, so 7.15, which is Mexico. And then 1.83, which is India. That's less, so 7.15 is bigger than 1.83. Then I can order them all together. So literally the order goes United Kingdom, because 1.06 is the biggest. Then I have 1.03, Canada. My next is going to be 7.15 times 10 to the 6th. 6th is less than 7. Mexico. And I probably should do that in a different color. And then I've got India last, 1.83 times 10 to the 6th. If you cannot do this by just looking at the scientific notation, move those decimals and order them like you would normally with regular old real numbers. So I want you to go ahead and try this out on your own. Pause the video, try it on your own. When you come back, we'll have the answer. Boom, a bunch of stuff should have shown up on your screen. If you look at this, I have started with my Las Vegas and my Los Angeles. They both have a power 10 to the 6th. So here's those two right here. I put LA on top because 2.2 is greater than 1.3. So I know that LA is going to be my greatest amount. Next is going to be Las Vegas because it is just less than 2.2, but it has the same power. Now let's look at DC. DC and Boston both have 10 to the 5th power, meaning they're going to have the same number of decimal places after their, or same number of numbers in their whole number of digits, I guess is what I'm looking for. So 9.01 is bigger than 7.21, so that's going to come next. And last but not least, old Boston with 7.21. So again, looking at my exponents first, then ordering those decimals from greatest to least. Try this one on for size and see what you can do. Actually, no, you don't even need to try it on. If you could walk at a rate of 2 meters per second, it would take you 1.92 times 10 to the 8th seconds to walk around the moon. Is it more appropriate to report this as scientific notation seconds or this many years? Well, obviously you're going to want to represent it in years because that makes more sense. The unit of measure makes more sense. Try this one and see what you get. Which way would you represent this particular answer? Would you represent in scientific notation or would you represent in regular standard notation? Pause the video and see what you come up with. When I paused it, I realized that my entire face was over the answer, or was over the question, so it's probably hard to do. So, in this case, when you're talking about the ocean floor moving 475 kilometers over 65 million years, would you represent it in scientific notation, or is it easier to understand if you say 7.31 centimeters per year? 7.31 is better.